Our next speaker is Professor Kaspar Althoefer. Hopefully I pronounced it correctly. So he's one of the leading authors, most cited researchers in software robotics community. I think it's the top 3 or top 5 highly cited researcher in software robots. And Professor, can you share your screen and start your talk? Thank you.
Yeah, thank you very much. Thanks a lot for having me. I think it's a fantastic workshop. I'm very pleased to be here, and I think we should have more of these kind of workshops where we actually talk about, you know, the tips and tricks behind the systems, and possibly also talk about problems that we have building our systems. So thanks for the introduction. I'm from the Center for Advanced Robotics at Queen Mary, and I want to talk about soft robots today, and also touch on stiffness controllability. So really, in the spirit of this workshop, I don't want to go into too many details. So I'm interested in soft material robotics, and I will focus on 2 parts of the work we're doing here. So it's soft silicon rubber bots, as I call them, and inflatable bots. So we take inspiration from the Octopus, which you can see here. So I think a fantastic animal, no bones in there. As you can see, very flexible, very compliant, very squeezable, capable of going through very narrow openings, but at the same time also able to apply forces to the environment by stiffening the muscles in their bodies and tentacles. So looking first at those soft silicon rubber bots that we are working on, I have to go back a bit in time. So the work started in the framework of an EU project, and the idea was to create these soft and stiffness controllable systems for minimally invasive surgery. And so from that, the work started. And it was nice also to see the work by Professor Tsuchimori, who gave us a lot of inspiration. So we created devices very similar to what he has also been working on for many years. We started with systems that looked more like that, and we were not so happy because there was a lot of ballooning happening. So here we had just silicon tubes, and that had chambers inside, and we filled them with air, so they were bending nicely, but that was not really what we wanted. So our first approach there to overcome the problem of ballooning was to actually put a mesh on the outside, as we can see here, and that kept everything at bay. And so we could bend our devices, we could elongate, we could apply forces to the outside. And as you all know, these devices are fairly robust towards kind of forces from the outside. So that worked quite well. We had our first prototypes, and I show here one example of one of our segments. So 3 air chambers inside, and then we are using a joystick to operate that. But that was not really what we wanted. And even though we could avoid the overall ballooning, the ballooning was kind of happening inside. And when you have multiple chambers or multiple actuators inside one of these robot segments, then they influence each other. So that was really not good for the performance of these systems. So we decided then to look into fiber reinforcement and to apply that, a fiber on the outside of these chambers. And that really improved things quite a lot. So as you can see here, this is the non-actuated state on the left-hand side. On the right-hand side, we push air inside and we get really a nice linear elongation. And then we can put multiple of those actuators together. As you can see here, for example, on the right-hand side, you see now 3 of them together, bundled in a silicon rubber form. And when you actuate now one chamber, then you achieve that kind of bending. And that led to further development. So you can see here the CAD drawings for the molds we created. So I should also highlight that. So we were really using molds here. It's quite a while ago, and 3D printing was of course available, but 3D printing flexible materials, soft materials, was not really an option then. And so we created these molds that were then filled with silicon material that could cure in those molds and be turned into these kind of structures. So you see here in gray the silicon material. We have a central area, a hollow space to feed all kinds of things through. And these are now these fiber reinforced chambers. So as we can see in this case, we work with pairs of chambers. And so we have 3 pairs all around. And these chambers can be now actuated. And when they are pressurized, then they start elongating. And because everything is kept together in this soft structure, we achieve bending in one direction. And yeah, I have to mention in this context my PhD student Jan Fraas, who has been really involved quite a lot, and I will mention him quite a few more times in the coming presentations. Now, what you might say is, okay, that is nothing new really. Others have used fiber reinforcement for their pneumatic chambers. So the point I want to really highlight is the fabrication process that we are using. So what we are doing is we are rolling up, winding up the fiber before we start any messy work with silicon material. So many others at first create a silicon structure and then apply the fiber to that. And that makes things actually more complicated because it's more difficult then to apply the fiber. Here in our case, and I want to go to the next slide shortly, we just have a spindle, so that is an electric screwdriver if you want, and the fiber needs to be just fed to now our interior part of our mold, which is here shown in blue. And now we have, it's a matter of like 5 to 10 seconds that we have the whole fiber, the helical structure created on our mold insert. And if I go back again, so that is then stuck inside this first mold that is filled with silicon. After it is cured, it's taken out, the mold is being removed, and you create now an empty space in the center that you fill now with silicon. So in this way, you apply the silicon from the outside. Once you have it, once you have applied your fiber or put it into place, the fiber, you apply the silicon from the outside and then apply it from the inside. And that makes the process so much more rapid and much more accurate as well, because now we have a very well applied helical fiber structure that is sitting in the wall of our inflatable chamber. And Jan Fraas, I have to mention again. So here you can see now how these things are being put together. So we have here the outer mold, and inside we have the multiple actuator chambers with their fibers on them, and that is then filled with silicon material, and a lid is put on top. And here's another view where we can see how the silicon is kind of formed around the inside chambers. You see here in a slightly darker black, these chambers sitting inside our structure. And that allows us to make nice robots like these. Can you hear the sound from the video? You can hear it. I don't want to, I mean, it's not there for you to hear it, but never mind. I mean, it shows that we use, of course, a compressor, a problem that was highlighted beforehand. You see the blue chambers there, blue tubes that feed the air into these robotic devices, which actually work quite well. As we can see here, very robust, very nicely controllable. We are using actually a PlayStation to control them. And that can be also further produced towards, further developed towards now the, the creation of robotic devices that can be used for keyhole surgery. here we are inserting one of our robots, which is made up of 2 of those segments inside a replica of a human body. So it's a phantom. It has a camera at the tip that gives the images that we can see on the top left. And we can now move inside and use the actuation, use the dexterity to move forward and move around obstacles that are possibly in the way. The same principle has been now applied here as well. And so you can see now the same kind of approach taken to create a robot arm that could be possibly used in manufacturing. We have 2 segments in the main body, the top segment and the lower segment. Each of them has 3 pairs of chambers that can be actuated to achieve that movement. And again, the same principle applied again also in the robotic fingers. Again, we have now these chambers built in. These are fiber reinforced and allow us to carry out very robustly these kind of grasping movements. And I mentioned Jan Fraas a few times. He also is in charge of these hands that we have developed. Again, the same approach is taken. We have in blue stiffer material, stiffer silicon material, and then integrated with that these chambers. So in yellow, again, the same kind of chambers, and they have this fiber reinforcement, and this time it's in yellow, to make them elongate in a linear fashion. And we can see that here in action. And so we have our robot hand here, and it is now controlled by a leap motion input device and gives quite natural movement, I think. A few more examples on that. So here we have moved forward and created now a kind of a tentacle, and that is now based on the same principle again. The only thing we have done here is we have split the chamber into 2 parts. So you have one part here and another part there, and you can see again the fiber reinforcement. So that allows us to create now these dual chambers combined together, and we have now much more control over the arm that it's attached to, and we can see that here in action. So we can now achieve different movements depending on how we control now the air that is going into these chambers. So we can also now control the way we actuate the various chambers, 8 of them in this Octopus phantom. And we can also control the stiffness in these chambers. Now, I'm coming back to this diagram, you think, but actually here we're trying something new now. So instead of winding the fiber onto a rod, we are actually trying to print now the reinforcement. So we want it to be part of the production process to make the production even simpler. And Jan Fraas has also worked on that. So I have to accelerate a bit, I have the feeling. So we can see here now plastic fibers being printed. So for example, from PLA or from nylon. Nylon gives better results because it is more flexible. And so these actually remain in there. So the trick here is to actually have a scaffolding, which is on the outside. You can see it with those hooks, sticking out, holding the rings in place during the process of producing it. So the structure is printed, silicon is poured in, and then you destroy the outer scaffolding, and what remains is the no, this video doesn't run because, just give me a second. So now I should be able to run it. So here you can see the printing process, and that is all what is needed. You need to just print this structure, pour the silicon in there, and the only additional step is to put then caps on either side. As you can see, you just print it, so anyone can do it who has the CAD drawings and can create then pneumatically actuatable soft robots. You don't get it totally for free. We have compared that to our fiber reinforced systems, and as you can see, that bends very nicely, even at high pressures. while if we increase the pressure too much in our new system with the printed fibers or printed reinforcement, then there can be this ballooning effect. But you can also get more information on this website there. Jan has a very nice website showing all what I'm showing here today. So I have only a few more minutes left, so I show quickly that we also worked on stiffening these devices by introducing tendons that are integrated with what I've shown beforehand. We have our soft robot actuators with the fiber reinforced chambers, tendons integrated that can be motor controlled, and we can now pull against the air that goes into the fibers and create a stiffening. And that was done by Ali Shiva, so for the change someone else. And we could show through some experiments that actually the stiffening can be increased in this way. I have just only 1 minute left, it seems. So we have also developed fabric-based robotic arms, and these are inflated by air. And the interesting thing here is they are inherently antagonistic. So we push the air in and use tendons to pull back. So this antagonistic behavior allows us to navigate them, and we can also see how they can inflate and they can also deflate. And once we are in the space, we can use tendons to steer them. So we can, with this approach, we can navigate and change the stiffness at the same time through the air pressure and the tendons operating in the other direction. And we have turned this to inflatable robots and inflatable endoscopes, as we can show here. And I can now stop at this point, or maybe just give 1 more minute to one other system we have been developing. No one is complaining, so I just quickly jump to the inflatable stiffness and stiffness controllable systems that we're also developing. And so here we are just creating links that are made from a silicone material and a mesh wall, and use that to actually integrate this with robot arms that have a very standard structure, but can now control the stiffness. And so we create something that is very safe, because if need be, we can reduce the stiffness and make it safe for human-robot interaction. And that is our response to the series elastic actuator, SEA. I think I should stop now. So thank you very much.
Yeah, thank you for the amazing talk and the impressive demonstration.